My name is Mika Peggers. I'm a product marketing manager here at Rescale, and I'll be your host for today's discussion on the age of simulation-driven design, going beyond CAE analysis with design of experiments and optimization. Presenting today, we have Peter Liu, who is a solutions architect here at Rescale. Peter will go over the differences between a standard simulation, design of experiments, and optimizations in numerical simulation, review some of the challenges and opportunities in each, and give a live demo on how to implement them on the Rescale cloud simulation platform. Before we get started, I'd like to go over a couple of housekeeping items. First off, we are recording this webinar, and I will be distributing the recording later this week. And secondly, if you have questions during the webinar, please make sure to type them into the questions section in the GoToWebinar panel, and we'll address these at the end of the webinar. And it's better to type those in earlier rather than later. All right, Peter, if you're ready, take it away.
All right, thank you, Mika. First of all, thank you all for joining us today. In this webinar, we're going to talk about how you can go beyond a traditional CAE analysis by combining techniques such as design experiments and numerical optimization with Rescale Cloud HPC resource. So to start, let's just take a quick look back of the CAE industry. So simulation has really come a long way. Starting from the 60s, using analog computer, you see on this picture here, to solve differential equations for vehicle dynamics. Then to the 70s, where finite element analysis started in the aerospace industry for structural analysis. Then to the 80s, automotive industry began to run crash analysis on CAD models to really reduce the cost of crash testing. Then to the 90s, computation fluid dynamics, or CFD, for combustion and aerodynamics really started, and combined with an explosion of high performance distributed supercomputers pioneered by CAE. So today, CAE engineers now run high fidelity multi-physics simulation, perhaps with tens or hundreds of millions of cells or degree of freedom, routinely on HPC with thousands of cores. So on top of that, techniques such as design experiments and optimization really drive the need for more computation power to deliver answers in a timely manner. So in this webinar, we're going to take a look at what is the benefit of those techniques and why cloud computing is a perfect fit for design experiments and optimization. So before we dive into design experiments, let's first take a step back and look at what is a simulation. Now, let's say you want to understand the stress distribution of the engine block. So what you do is you create a model, which essentially is a digital representation of your physical engine block. And then you feed in some inputs, which can be your boundary conditions such as temperature, loads, material properties, or maybe the geometry size itself. Then you run this simulation. You can use software, commercial software, maybe ANSYS, APCUS, or other open source software, and which all of them essentially is solving the governing equations that describe this physics here. Then from the model, you extract some quantity of interest. Perhaps you're interested in the stresses, the displacement, or maybe the fatigue criteria of this geometry here. So what this is a workflow of a single simulation going from an input to your outputs. Now, let's take a step further. So if you think about an engine block in an actual car, well, it is not going to subject to a single load. You may want to test perhaps hundreds of different load conditions to understand the performance of this engine block. And that is where design experiments, or often shortened DOE, come into play. So design experiment is essentially a systematical way to determine the relationship between the inputs, such as load conditions, to the outputs, in this case, let's say stresses. So with that information, you can then manage the input in order to find perhaps the optimized output. All right, back to this engine block example. So let's say you want to test 100 different load conditions. So you want to subject to 100 different forces, things like that. Now, of course, you can do it manually. So what you do is you set up 100 different simulations. Well, but that would be a very inefficient and time-consuming process. So what Rescale offers is it allows you to set up all those simulations in a single DOE run. So in that case, let's say you want to run 100 different load cases. So you can feed in those all 100 load cases all at once, and then get 100 different type stress outputs on your output. So that's essentially the high level what a design experiment means. You have a variety of the input conditions you want to feed in, and you want to investigate what is the responses, what does the output look like based on your input results. All right, now let's take even a step further. So let's say now, instead of running of a design of experiment, we're interested in to run a optimization. So what is the optimization? Again, let's take this engine block example here. So in the content of optimization, the input you see here, temperature, loads, etc., essentially is the design variable that you want to vary automatically. So these are the design variables. And then to optimization, the analysis in the middle can be just mostly treated as a black box. So this is, you just feed something into this black box, which solves whatever given equation behind the hood, and then you get some output out of it. So the output in this case would be considered as a objective function. Perhaps you want to minimize or maximize the, or minimize the stresses, or you may want to set up some constraints. Perhaps you want to make the stresses is less than the yield stress, or the fatigue criteria is less than a certain amount. So the output you get from that black box is your objective function and constraint. Now, what the optimizer does in this case is to close the loop. So this is the workflow on the top is a single iteration of a optimization. So you feed in some design variables, the initial design variables, you run this through the black box, you get some results. Those results will feed into this numerical optimization algorithm to determine what is the next set of design variable to try. So in the end, the optimizer will drive this repeated analysis. You may run maybe tens or hundreds of this black box or whatever analysis in the middle in order to find out what is the optimal set of design variables in order to achieve the objective function and meet the constraint that is specified. So that really is what, on the high level, what is a optimization. So just to show you a real world example of why we want to interest in optimization. So let's take an example from aerospace industry. So let's say you want to study the shape of the wing of an aircraft. Now, what you would do basically is you run a CFD analysis. But before we do that, let's say you sit on the window seat of this aircraft and you look at the wing, and the shape of the wing looks something like this. Now, without any kind of engineering analysis, you can pretty much tell from your intuition that's not going to be a good design. So if the wing looks wrinkles like that, you probably don't want to be on that aircraft. So if you look at the wing, the shape of the wing looks like this. Well, it looks very smooth. It looks like a kind of a supercritical airfoil shape. Then you probably will say, hey, that's probably a good design. So that looks pretty good. It's very streamlined. It looks very smooth. Now, what about this? What about we look at a design which show in blue here? So if you look at the difference between them, you probably wouldn't notice much difference at all. But the blue shape here is the shape that's developed or designed by the optimization algorithm. Now you can see between them, it only have very, very subtle difference, which you can't really perhaps perceive using human eyes. But between them, if you run a CFD analysis on top of that is actually about 5% difference in drag, subject to the same lift constraint. So in terms of the lifespan of the aircraft, that translates to about $2.6 million per year in fuel saving. So hopefully you see that the subtle difference between a kind of engineered design airfoil to a numerical optimized airfoil can be potentially have a huge impact. And that's really show you the power of numerical optimization. Now, going beyond that, perhaps you can even go a step further, such that you can, instead of starting from an airfoil, you can even start with any geometry. So the holy grail in optimization perhaps is to start from any shape, maybe a circle with the right amount of boundary conditions and the constraints and the right objective function. You can turn that circle into a wing through numerical optimization without any kind of a human interaction in the middle. And that's what I would consider still a research topic, but that's really show the direction of the industry is going toward. So perhaps you want to start with a sphere with a few clicks of a button. You can tell the optimizer, I want an aircraft with 1,000 nautical mile of range with this performance, and it will turn that sphere into the right shape of the aircraft and optimize the whole geometry. So perhaps for the engine block, you will start with a chunk of aluminum in geometry, and with the right amount of settings and conditions, you'll turn that into an optimized engine block shape and given the right conditions. So that is the direction that you can see the benefit here is that it will give you a turnkey solution that give you the optimized design at the end. Now let's think about how Rescale can help in this case. So Rescale has a Scale platform that offers a very simple, intuitive user interface to help you set up your design experiments or optimization directly in your browser. So with that, you have also access to about more than 220 different simulation software that is tuned and available on the platform. So you don't need to do any kind of installation. So you can just pick whatever software title that you want to run in your DOE or in your optimization. In addition, the user have access to a global network of data centers and supercomputers. So I'll talk about in a minute why this is important. So with that, you can pick the best suited architecture, the best data center based on the simulation you're running. So you may wonder, why do we need to pick different architecture and then on the back end? Well, if you look at any kind of analysis, each analysis actually has a different requirement for the hardware. So let's say if you're running, say, Abacus, perhaps you want a server, you want a cluster that has higher memory. If you're running Star CCM or CFD, you may be interested in InfiniBand connected clusters. So perhaps you're running ANSYS Fluent, you want to try to take advantage of a GPU acceleration. So each of those can give you different hardware configuration. And running on Rescale, you don't need to commit to any hardware. You can provision hardware on demand, and you pay as you go. So let's take a look why DOE and optimization is very important, and then why the HPC resource is the only way to unlock running large-scale DOE and optimization. So again, let's go back to the engine block example. So I said earlier, we have this single workflow where you have this input, you feeding, you get your model, you get your output. Now let's look at a hardware resource behind the hood. So let's say you bought this brand new cluster that costs about 100K, and it has 128 cores on the cluster. And this particular model, let's say it's a high fidelity model that takes about 12 hours to run on this hardware here. And this is a single analysis where you go from input to your output. That takes 12 hours. Just make an assumption here. All right. Now let's see how we can use this hardware and going into design experiment. And again, let's assume the same design experiment that we're interested in. So we have 100 different load conditions we want to test in this design experiment. And we're going to feed each of those loads into the cluster that we have. Now, because this cluster only has 128 processors, so you'll have to run each of those load conditions in sequence. So you'll start with load number 1, then run load number 2, then all the way to load number 100. So, and this basically you're solving this design experiment in sequence. So with the hardware that we talked about earlier, that would actually take about 1,200 hours to complete solving this DOE model. If you look at 1,200 hours, that's roughly about a month and a half. And well, I don't know about you guys, but I don't think most people wouldn't have that patience to wait for the results to come out for a month and a half. Ideally, we want to maintain it to like 12 hours so you can run overnight or over the weekend and you get to the results next morning. So There's a couple of ways you can fix this. So let's say instead of using this 128 core, perhaps you can say maybe we can expand our cluster a little bit to add more cores so we can run all those models in parallel. So if we expand the cluster and then allow everything to run in parallel, we would need a 100 or a 12,000 core cluster, which will actually, let's assume just a linear cost between the cores and the cost. It's going to cost about $10 million for this cluster. So with that 10 million cluster, you can cut the runtime to 12 hours. But if you think about this cluster, it has so many cores, most of the time it's going to be sitting on idle. So only when you run these large scale DOE and optimization where the cluster will be fully utilized, most of the time it's just sitting there idling and consuming electricity in a way. And that's really where cloud computing comes to play. So you don't want to commit to any hardware in advance, but instead you want to use HPC hardware on demand. What Rescale does for each of the load conditions when you set up DOE on Rescale, it will provision a mini cluster or a private cluster for each of the load conditions. So let's say we're going to use, again, 128 cores for each load condition. Then Rescale can provision 100 different those clusters for each of the load conditions. And then you can run all the load condition load cases in parallel. And you only pay as you go. So when you're not running these large scale DOEs, you're not provisioning any cluster, so you don't pay anything at all. When you do use it, you just pay whatever amount of core hours you use on these machines. So with that, that really showed the benefit of using cloud HPC to run those large scale DOE and optimization. Otherwise, you'll be committed to a very large cluster and then using the on-demand resource that can provision cluster on demand. So what I'd like to show you here is just to show you how you can set up a DOE on Rescale. All right, and I'm going to use this T-junction pipe example here. So assuming we have this T-junction pipe, and then this is a very common geometry that's commonly used in the industry, so where you have some fluid coming on one end and some hot fluid coming to the other end. And we're going to model this using ANSYS Fluent. And the inlet condition is going to be varying. So the goal here is to find out what is the outlet temperature based on the combination of inlet and hot inlet and cool inlet condition. So the design sweep or design experiment we want to study here is that we're going to specify a all combination of cold inlet and hot inlet temperature and to see what is the response of all that temperature look like by running all those CFD analysis in parallel. All right, so let's go ahead and move to Rescale Platform to set it up. Okay, so before I jump into design experiment, I'm going to start by showing you how to set up a single analysis job. So on Rescale, once you log into the platform, you will see a list of simulations that you have run in the past and a list of simulations that I have currently running. To set up a new simulation, you click on this new job button. And by default, it will pick what we call a basic job type, which is essentially what I described as a single simulation run. So if you remember the flowchart I showed earlier, so you have some input, which is your model file. You run it through some software under some hardware setting, and then you get some outputs. And let's just quickly show you how you set up a Fluent CFD model. So if you have your case file or model file sits around on your computer, you click upload from this computer to upload the model file. If you already uploaded the model to Rescale before, you can use pick from cloud storage. All right, I'm going to pick those two models. So the case file describes the boundary conditions and setup of the model, and the journal file describes how you're going to run this model. And then going to the next step is to pick the hardware. So on Rescale, we have about, like I said earlier, 220 different software available on the platform. So you can easily just pick the one that you're going to use. And in the case of the CFD problem, I'll go ahead and pick ANSYS Fluent. Once you select the ANSYS Fluent, then you can see the command to launch the Fluent in batch mode. So what the user really need to do here is to go in and change the name of the input file to the actual name of the file we upload in the first step. And I'm going to use the on-demand license here for the license option. All right, and then going to the next step, and this is where you can pick whatever hardware you want to run. And I said earlier, each simulation runs differently on different architecture. So you can take a look at all those different available core types on the platform and make sure you always pick the most appropriate core type based on the simulation you're interested in. This is a pretty small Flint model, so I'm actually going to just use the Onyx core type, which is a Haswell chip with 2.9 gigahertz and about 3.3 gigabyte of RAM per core. So once I pick the core type, I can go down to below and pick how many number of cores I want to use. So in the case of this model, like I said, it's pretty small. So I'm going to just use, let's say I'm going to run with 4 processors or 4 CPUs. All right. And then going to the next step, and this is where you can add a optional script to post-process the results. We're not going to use it here, but we do going to use this for DOE in order to visualize the data. So let's skip this for now. And all the way to the last step, submit. So once you review everything and it all looks good, and then you click submit, which will start this simulation here. Now, this is what we consider, like I said, is a single simulation that goes from the input, run the analysis, and to the output. So while this is starting, let me just show you what about design experiment. So on the platform, by default, we'll start with this single analysis, but you can go into the job type and switch to this to DOE. And say yes. Now you'll see this template change a little bit. So if you remember the chart earlier, this will look very familiar, where you basically have a number of different load conditions or whatever boundary conditions under this parallel setting, and feed that into the software here, and it's going to spin up and running all those in parallel. And then in the end, you can have a Postgres script to combine all the results back into a single plot, for example. All right, just to show you how to set it up. So let's start with the input file. Again, if you have it on your computer, you use upload from this computer. If you already upload to the cloud storage before, I'll use file from cloud storage. And I'll pick this DOE case file. All right, as selected file. So this is essentially the case file that, again, describes the boundary conditions, which is the same file as we showed earlier. And let's go to the next step here. And this step is where you define the different load conditions that you want to test or try on this DOE. And there's a couple number of ways you can define it. You can define that in an Excel spreadsheet and then upload that the CVS file from the spreadsheet. Or you can define it directly on the platform, which we're going to do here. So you can define a cross product that generate a table of values to try. Or you can use the Monte Carlo, which define whatever certain distribution and feed those data into the model. So in this case, let's say I know the combination of hot and cold inlet temperature that I want to test. So I'm going to go ahead and specify the hot temperature that I want to try. So I'm going to say I want to try with 320 Kelvin to 350 Kelvin with the increment of 10. So that gives you 4 data points here. Click add. And then we can specify the range for cold temperature. So I'm going to say cold. I'm going to define this variable cold temp and start with 250 and then all the way to 280 with an increment of 10. Again, that will give you another 4 data points. So in total, when you do the cross product, that will give you a total of 16 different load conditions that you're going to run on 16 different simulations. All right, now we have specified the parallel settings. Let's go to the next step, which is define the template. The template means that you will take the value that's coming out of this parallel setting and then put that into the model to run. So in the case of ANSYS Fluent, that's going to be putting into a journal file that you're going to drive the simulation. And again, let me go ahead and pick from the cloud storage. So this is the template that we define here. And then let me change the name of the file so it's a bit easy to remember. So I'm gonna take the template value here, and then once we change the value, and then you'll rename it to run.glu, and then this is the journal file that's gonna drive the simulation. So if you look into how it is defined under this journal file, let's go ahead and edit it. This journal file looks very similar to the journal file that we used earlier for a single analysis, except you see there's 2 lines here. In these 2 lines, where it is going to change the boundary condition for the cold inlet and hot inlet. And typically what you have is that you will have a value here which defines the cold temperature and a value here that defines the hot temperature. But since we're running a DOE, instead, we'll put a placeholder that references the variable that we defined earlier. So earlier we defined the variable cold temp. Now you use this $sign to say, I'm going to put the value that coming out of that cold temp variable and put that into this text file here. Similarly, we're going to take the value of the hot temperature that we defined early and put into here. All right, so with that pretty much fully defined the model here. So again, it will take this template, putting the right value, and then rename it to run.glu, and then put it into each of the mini clusters or parallel clusters we're gonna run. Okay, so we have the input file, we have the parallel setting, we define a template. Let's go ahead to the next step, which is similar to the single simulation analysis. This is where you pick the analysis tool you're gonna use. Again, in this case, I'll use ANSYS Fluent. And similarly, you'll see the batch command to launch the Fluent analysis. And in this case, we name our journal file run.glu, and I'm gonna put the name here. Just to point out, we do support a wide variety of versions of each software. So you have a drop-down list here that you can pick whatever version you like to use. So for this demo, I'm gonna use 18.2, which is the latest version right now. All right, so again, on the license option, I'm going to use the on-demand license. I do forgot to mention that we can connect with your license server. So if you already own a software license, do direct connection to your license server, and then it's going to check our license from your license server. All right, so pretty much we have set up most of the model steps. Let's go to the next step here, which is the hardware setting. And again, this page looks very similar to the single analysis run that we showed you earlier, except if you look all the way below, it has some additional setting here. So the first setting, number of cores per slot, means that how many processors you want to use to solve a single analysis. Again, this is a very small model. Let's use 4 processors to solve a single model. The number of task slots means that how many models, how many DOE runs you want to solve in parallel. Let's assume we want to run everything in parallel. So in this case, it's going to be 16 different combinations. So we're going to say we're going to run 16 different slots to run all the DOE variables in parallel. So one interesting thing about the on-demand HPC resource is that it doesn't matter you run it in sequence or in parallel. The hardware cost will be exactly the same, because how Rescale essentially charge is per core per hour. So if you run all your model in sequence, it will have the exact same per core per hour or core hour usage versus solving them in parallel. So you might as well try it to run everything in parallel. That will give you a much faster turnaround time. All right, so we have set everything up here, and then let me go to the next step. All right, so this step is where you can add a post-processing script to pick out the results. So remember, in the problem definition, we want to find out what is the temperature looks like for a certain combination of the inlet and outlet, or cold inlet and hot inlet temperature. So what we can do here is we can add a script to pick out the results from a log file that you run in the model, to find out what is the outlet temperature after each run. So what I'm going to do here is I'm going to pick this script that I developed. So let's add it. And just to show you what it looked like, it's essentially a bash script to pick out the results for outlet temperature from a long file. So it's very simple. It can be a bash script, and can be a Python script, so anything you can run, it can be added here. And it will specify the command to run the script, which is the output extract.sh. All right. So with that, I believe we complete all the settings that relates to this model. So just to recap, we start with the input, which is the model file. We specify the parallel setting, which is what is the variable that you want to sweep through. We define a template that takes these variables and put that into the analysis model. We pick the software package you're going to run. Then we pick what kind of hardware we're going to use. So we're going to run everything in parallel. So we pick, spin up 16 different clusters. Each cluster has 4 cores on it. And then finally, we'll add a post-processing script where we can pick out the results from those models. So once we complete all those steps, we can go ahead and click submit. And then your job will be running. Well, one of the nice things running on a cloud is that there's no queue time. So if you ask for 1 processor, or if you ask for 1,000 processors, all of them will start right away. There's no scheduler, there's no queuing. So once it's started, it will take a few steps to spin up a cluster. So the very first step is validate the input. And what it does is it's going to check the syntax on the command, and it's going to also check your account, make sure you have the sufficient budget and the permission. Then it'll go provision these clusters. So it's going to spin up those clusters, and then it's going to load up the input files onto the cluster. And the third step is running the job. And this is where you are solving your model. And all the way, once all the model has been completed, it's going to transfer all the results back to cloud storage, and then shut down all those clusters. So these are the stages you can monitor while your job is running. So while this job is starting up, I just want to quickly mention that there's a lot of additional functionality you can try. So for example, if you like, you can easily share this model between your colleagues, so they can see all the input and output file associated with this model, as well as the same monitor screen as you're seeing here. So it's very easy to share files and share jobs between. If you want to create a new job with a very similar setting, you can simply click clone button, and it's going to spin up a brand new job with the same setting that you can monitor, maybe tweak a few other different settings, and submit it again. At this point, you can completely shut down your computer or close your browser, so it will still running on the cloud. There's no need to maintain your browser to keep it open. All right, so while this job is running, let me just quickly show you what it looks like once it's completed. So I'm going to show you this model, which is exactly the same model which I ran earlier. So going back to the steps here, so what you see here is the same setup as we go through earlier. Then going to the status, this particular model is actually very small. So since we're running everything in parallel, it only takes 3 minutes to complete all those 16 different simulations. And in the results section, you can look into the details of each run. So as you notice here, we have a total of 16 different runs. And each run, you can see the starting time, the complete time, the duration. Because the different boundary conditions, duration is slightly different between them. And you can see the variable that we feed it into. This is the cold temperature, hot temperature combination, and that's what the outlet temperature look like based on this inlet here. You can even click into each of the runs here, so to look at all those different files. So for example, if you want to make sure the model convergence looks good, perhaps you can quickly take a look at the log file, just to make sure the convergence history looks fine here. You can download each of the individual data files and for post-processing, or you can download everything back to your computer. All right, so going back to the setup here, let me see if the other job has started. It's still starting right now. Just going back to this model file again. So once it's completed, because we wrote this post-processing script to pick out the data, pick out the outlet temperature here, you can even do some very quick post-processing while you're on the platform. So for example, you can go to this chat or chart section. So perhaps what I want to find out is I'm going to put run as x-axis. And then let's say I'm going to use plot all those three different temperatures. So you can see the cold temperature, the hot temperature, and then what does the outlet temperature look like based on each of the combination here. Maybe I want to look at the contour plot. So let's say I want to see Z as outlet temperature and XY as hot temperature. So you can see for each combination of hot and cold inlet, what does the outlet temperature look like as a contour. You can even do 3D plots. So for example, here with this setting, you're seeing the outlet temperature as a function of cold temperature and hot temperature plotted in 3D. So this essentially gave you a kind of a response surface that with the next time you can come over here and look at the cold and hot temperature, and it can help you predict what is the outlet temperature will look like based on this response surface. All right, so hopefully that gave you a quick overview how you will set up a design experiment model on Rescale. And once the model started, just to going back to that model, you can see each of those runs and monitor the intermediate progress. So for example, I can look at run number 2, and you can monitor the convergence. And we call this live tallying, where you can monitor the screen, and this screen here will be updated live as your simulation is running. All right, and you can even log into the compute node. So we support direct SSH from your browser. So if you want to do more fancy stuff, you can even log into each of the compute nodes here and look at the results. All right, so let me go back to the slides here. So again, hopefully this gives you a quick overview what it looks like to set up a design experiment on Rescale. On top of that, we even have a optimization framework that allows you to set up a optimization directly on the platform. So this is what the flowchart looks like. It's very similar to the diagram I showed you guys earlier, where again, you have optimizer sits on top, which drives analysis here. In this case, I pick ANSYS Fluent. And you can have any kind of commercial optimizer or your own optimizer sits on top to drive the simulation. And once that loop converges, it'll spit out the optimum design at the end. And to change this to a optimization setup, all you do here is under the new job setting, you click job type, and then you switch that to optimizer, which will switch our platform into a optimization framework where you can go and set up your optimization runs. All right. So on top of that, you may be interested in to do a scripting where you want to drive your optimization algorithm directly from your computer and submit your job to Rescale. So actually, Rescale is built completely on top of API. So anything that you see I did on the platform can be done directly through an API call. So when you log into your Rescale account, you can generate API key, where then you can call actually directly from the command line to do any kind of operation that I showed earlier. We also have a command line interface tool, CLI, that allows you to, it's a kind of a reduced version of API that allows you to easily manage your job directly from a command line. So with that, just to show you what it looks like. So I don't think we'll have time for demo, but just to show you what it will look like. So you can directly from your script to call Rescale API or CLI, which will submit each of the optimization iteration directly from your script, from your optimizer to Rescale, run the model, and then download the data back automatically, and then go to the next iteration. So you can script it such that it gives you a fully automated design optimization process. So you run your optimization on your own laptop or workstation, but then you're offloading all those heavy computation where it's solving large-scale models to Rescale Call HPC to leverage the computational resource behind the hood.
I guess we'll wrap things up here. Thank you, Peter, for presenting, and thank you to our audience for attending. And we'll see you next time. Thank you.
Thank you.